Quadratic functions and applications. Lots of applications of quadratic functions. One, these are three forms that you should know and have known for a few years now. One basic one is projectile motion. A projectile is an object flying through the air. Its motion is determined by gravity and its initial launch. So a rocket with a rocket propulsion or an airplane are not projectiles. Okay, a ball, a flying rock, anything that doesn't have, as soon as it leaves the table, yes. So one of the keys with projectiles is they do not have wings or anything that adds force other than gravity. Yes, there is air resistance. We usually don't account for that. Um, so here they've got the path of this ball being thrown between two boys, it looks like, and they gave the quadratic function that models it. Eventually, we'll be modeling quadratic functions with x and y separately over time. I did a tiny bit of that in pre-calc with parametric equations. That was the hard test. That was the really hard test. You'll get it this time. So, here, suppose the height in meters of a projectile above the ground at time t seconds after a launch is given by this quadratic function. From what height was it launched? That would be when t equals 0, that would be 2.25. So,
Oh,
yeah, sometimes they do that because they don't like the negative at the front. I just prefer to put the negative at the front. What is the maximum height reached by the projectile in a quadratic? How do I find the maximum? Yep, negative b over 2a, and I'll need to find the y coordinate. The negative 6.55 over 2 times negative 1.75. And then a, it is still,
that's
you can feel free to put it in the correct order. Yes. But yeah, the order is still there. So we could graph and find the maximum, which I think is what I'm gonna do because actually, yes, we can plug this in. Um, to find where ground level is, you'd set h of t equal to 0, and you could graph or use the quadratic formula. Actually, I don't want to use graph for this one because to find when it's its initial height again, it's 2.25 for h, correct? So it asks at what time will it be its initial height again? So these are going to cancel, and I'll get this, which I can then factor out a t on. Yes, which that would be the initial height. And so I end up with that part just going away effectively. And I can solve this.
way down.
6.55 over 1.75. Which I guess would be twice the time of this one, actually, which makes sense. Half of its time to get to that maximum height, half of its time back to get to the original height. And what time does it reach ground level? You're just using the zero, and we can use quadratic formula. Or we can just solve all of this by graphing. Honestly, with the graphing calculator, I would probably just solve all of it by graphing because I think it would have been quicker. Make one graph. So here's how they did a line at 2.25, found that intersection, found the zero here, found the maximum. And one graph could be used for all of those. Okay, here we have a model rocket launch straight ups. Forward from a platform 10 feet above the ground. The rocket leaves the platform with an initial velocity of 64 feet per second. The height above ground as a function of time t at the launch is modeled by this quadratic function. Use the graphs of the parabola to determine all of these things. Again, same thing. One of the keys to this equation the negative 16, this part is always the same for feet. It's negative 4.9 if it's meters. That 64 is the initial velocity. The 10 is the initial height. Okay. Here we have a tank filled with water. The value at its base is open, and the tank drains at a height of 8 centimeters of water remaining in the tank at time t hours. After the draining began is given by the formula h of t. So what is the initial level? How would I find that? You could just do h of 0 though and plug in 0. So it ends up being 8.25 squared. 65 something. What was the water level 10 hours after it began draining? So let's graph. Yeah, that one's just h of 10. 1 to the nearest hour, will the tank be empty? That would be this would be the 0. 1 to the nearest tenth of an hour, will the tank be 1/3 full? So let's just put this in the calculator. I'm going to show you a little trick on the calculator. Where's H? So I can actually just define my function. I need to use the colon equals. That's right. Okay. Now if I do h of 0, it evaluated it for me. H of 10. Wait, I might have taken the function wrong. It's positive. Well, since I entered it wrong, we're going to do copy and paste. H of 0, I think should be the same. H of 10. Yeah, it's going down. Okay. Now if I want to graph it, and it doesn't look like it's going down fast enough to be on here, I'll adjust my window. I know I started at like 75. Let's go to like 30. I don't know how far. I know I started at 75, or 68, so I'm going to say 75. No, I still have not reached the bottom by 30. Okay. Let's see if we get there by 100. Okay. I think I've reached the bottom. I guess. I think that's what this is supposed to be. Let's find when it gets to the bottom. Okay, 69 hours. It did ask when would it be 1/3 full. Oops. So 68.0628. I need to divide this by 3. 22.6875. So when I'm going to graph that as my second one,
Remember why we just took the initial volume and we like took a third of it?
yeah, I took the initial value, I divided it by 3. I'll find the intersection point. $29.06 What did to the nearest tenth of an hour, 29.1. But make sure to read those where it tells you to round. And I guess you could show all those points on the graph, or you could say h of 0 equals h of 10 equals, and that would be. But I think programming them in makes a nice shortcut. Okay, now we're on to cubic functions. So a polynomial is going to be any polynomial. What's the key to a polynomial? The exponents are whole numbers. Okay. All of the exponents are whole numbers. So which ones of these are polynomials? A and B are. It does not matter what the coefficients are. It just matters. C is 1/2. No, you cannot have 3 halves. You can have to the 0 power. This is a polynomial. Yes. This would be a constant, which is just 5. It can be negative. It can be an irrational number. Square root of 2 is a polynomial. It's square root of 2x to the 0, and that is valid. Okay, with cubics and polynomials, we're interested in symmetry. There's even polynomials which have y-axis symmetry sometimes. There's odd degreed ones could be odd if they have origin symmetry, which means they must actually, well, they don't have to go through the origin. There's a few exceptions. They cannot have y-axis and origin. And even f of negative x is equal to f of x. Which means on both sides they have the same y coordinate, whether it's 2 or negative 2. For odd functions, f of negative x equals negative f of x. And that origin symmetry means essentially 180-degree rotation of the right side of the graph, rotated 180 degrees about the origin. It has to be about the origin. It can't be about 1 or something like that. This does not actually have origin symmetry because this is not going through 0, 0. It's very close. It looks like it from the graph, but it doesn't. I thought it did from looking at the graph, and then I looked at the function and went, nope, nope, you don't. So sketch this. What is the transformation on this one? It's a cubic. What is this plus 1 doing?
Oh. Left.
So it takes my general cubic, moves it 1 left. I'm sure they want this point at 0, 1, which is the y-intercept, and negative 1, 0. Those are the 2 points I believe they'll want. This next one, we would go to the graphing calculator. Again, what points are they wanting? They say sketch a function. They want you to show all of the x-intercepts, the y-intercept. Remember, you get the y-intercept not via the calculator, just plug in 0 for all the x's. And they want the maxes and mins. A power function does not need to have the exponent just needs to be a real number this time, but it does not have multiple terms. They're going to take that form. Do you remember what makes a function an exponential function?
Independent variable, x is the exponent.
The variable's the exponent. Yeah, that's the key. And graphs of exponentials look like this. They have a horizontal asymptote, a lower one. Domain of exponentials is negative infinity to infinity. The range is whatever that lower asymptote is, which by default is 0, but if we add something like a plus c to the end, it becomes c. The y-intercept is whatever it's multiplied by plus the vertical shift. So here we have the graph. Find the value of p. So p is the y-intercept. How would I go about finding the y-intercept? That's the equation, yep. You could plug in 0 for x. It's 1 plus 5. Because it's 1 times 3 to the x plus 5, 1 plus 5. 6. Um, or you could plug in 0, 3 to the 0 is 1, 1 plus 5. This isn't a power function, this is an exponential. So now to find q, (81) equals 3 to the x equals 4, q equals 4. And you could solve that by graphing, or you could log that if you did. If it was one that you didn't know, right? Write down the equation for the horizontal asymptote. The horizontal asymptote is just y equals 5. It's by default 0. The plus 5 made it y equals 5. The graph is shown. Find the values of a, k, and c. They give me 1 point. Am I allowed to assume that c is 4 and k is 1? I think I have to. A is 6. I think I have to assume that. Because it looks like C is 4, right? And it looks like the y-intercept is 5, which would make the A 1. Yes. Okay, you are allowed to assume those things. So A was 6. I was like, I don't think I can solve it if I'm not allowed to assume those. The natural exponential function, that's e to the x. You will learn why e is so great when we get to calculus. So it asks me what the range of this is. The exponential function with e as your base. We've done that before. So what is the range of this particular function? No, 2 is. That's your horizontal asymptote. No, the y-intercept. The y-intercept would actually be 4 because it's 2 plus 2. 2 to infinity, yeah. And it does not include the 2. And finally, trig functions. You don't have to graph these by hand this year. You remember what periodicity means? Sure. Periodicity means it does repeat. The period is how often it repeats, or how much x or time goes by. So a periodic function is a function that repeats its values at regular intervals of periods. All 6 trig functions do. Um, they're going to graph out this wheel, which is kind of fun. But the applet. Oh, I can move the T. So we can see what that does, right? And this is angle versus position of point P. So it repeats. This one also repeats. It's an interesting function. Understand that they are periodic. This one is just a whole bunch of lines. You'd have to piecewise it. This looks like a greatest integer. I'm not sure which end is supposed to be open versus closed circle. This is a funky periodic. Looks a bit like a digital waveform. Um, technically, probably no. A lot of times we'll digitize waves and we will allow the vertical line to just kind of be there. Um, key things, maximum and minimum point. I called it center line in pre-calc, but principal axis is the center line. They just came up with the a harder way to measure period. I usually measure period from crest to crest instead of from a middle point to a middle point where it has to be going the same direction, both going back up.
Here.
You Period is usually thought of in terms of time. Wavelength is thought of in terms of distance. So on these, yes, but there are some applications where it's not the same.
Graph, my situations.
Yeah, it might be thought of as different. Yeah, like the wavelength of a light wave, if you're thinking of the period would be in the time it takes for one wave. The wavelength would actually be the distance it travels. We would graph those separately. You're aware of the unit circle and the sine function. Okay, with its amplitude, the default amplitude is 1, period. There's also shifts. I do not like that they're doing period in 360. Just convert things to radians. It's easier. Once you get to calculus, there are ways to do it in degrees. They are harder than converting to radians and converting back. And I would have to look up what they are. Um, so the difference between the sine and the cosine function is just that starting point. Cosine starts up at 1, 0. Sine starts at 0, 0 in the middle on the principal axis. So here, the radius of a Ferris wheel is 60 meters, and theta represents the angle measure in the anti-clockwise direction. That means counterclockwise. That's our normal direction from the x-axis. Find all the angles at which the passenger capsule is a distance of 35 meters above the axis. Give your answers in degree, correct to 1 decimal place. So the radius is 60. That means we have an amplitude of 60 on our sine function, correct? What I want to know is, did they shift this up, or are they saying the thing has a height of negative? Okay. So they've got our 2. Yeah, the Ferris wheel started, interestingly, the Ferris wheel started with you on the side for the angles. So they found the 2 angles by, instead of just by graphing, they just used the triangle method. Said, we've got a radius of 60, we want to be 35 high. We'll use the inverse sine. Do you remember how you get the second one? Because there's 2 spots where you're 35 meters high. It goes up past 35 and then down 35 on the way down. So the second one, because it's in this quadrant, I do 180 minus the 35.7. Um, the question I believe asked, I need to go back and read it. Find all the angles for which it is 35 meters above the x-axis. So it repeats every 360 degrees, right? Well, because we're in degrees, it's 360n. But because I'm in degrees, I must give it in degrees. You could write this as 60 sine theta and graph it, which is what they show here, and solve where it equals 38.5. They really failed at showing the plus 360n. But their question did ask for that, so does that make sense? That's kind of the introduction to function modeling. We'll be doing some more modeling. You have a quiz next Tuesday on 2.1 through 2.6. Nothing about that quiz is more than pre-calc. So that's it for today's lesson.